Okay, I think we'll go ahead and get started. So this is our second portion of the Swift, sort of a look at Swift and how it's going to work for us as a programming language. Obviously, it's still in beta. There are things about it that Apple has already acknowledged that they're going to change. There are lots of smart people now looking at the language and making suggestions to Apple for other things to change that we really don't know whether they will change. So everything we learn right now about Swift is uh, basically subject to change. I would assume the language is going to stay pretty much the way it is, but there will be some maybe not insignificant changes coming that will affect how we use the language to build apps. This week, what we're going to talk about is the control flow constructs, uh, their support for strings in the language, and the built-in collection types, which will be arrays and dictionaries. Um, and the general format will be just going through some demos in Swift Playgrounds, which is a feature of Xcode, which I'll show you guys in a few minutes. Um, and if you have questions as we go along, fire them away in the chat area, and I will do my best to answer them as we go. Okay, so let's see, a little blurb about us. Basically, Terry Tucker and myself, we are a small company called Focal Shift that does contract software development for iOS. We also do training classes under the name iOS Weekend, and that's what the meetup group is. And then we also do some local classes in the Bay Area. Excuse me. So last week we talked about literals, types, operators, and functions. Went through some playgrounds on those. I made all those playgrounds available to you on GitHub, and also um, showed you guys how to interact with Swift from the command line in the terminal. Um, Shortly after we finished our meetup session last week, Apple sent out an announcement that they had released a new version of Xcode. So everything that I did last week was Xcode 6 Beta 1. Now they have Beta 2 available, and Beta 2 is what I'm using now. Maybe today they'll announce Beta 3, who knows? So from last week, there is a video, and it is up on YouTube. And anyone who's in this session or the previous one is able to go get that video. If you try to access it on YouTube and you can't, if it tells you that it's private, you need to just get your email address onto the list of addresses that I've granted permission. So just send me an email somehow asking to have your name added. And I'm going to do the same thing for this week's video. Just put it up there. I don't know if they'll be that useful or not, but assuming they are, I'll keep doing them. Okay, so this week it's basically three things: control flow, strings, and collections. So let's get right into that. Okay, so what we've got is we've got a workspace in Xcode, and the workspace is called Intro to Swift Programming. And you can actually get at this same thing up on GitHub. Let me actually just make that apparent. So, oops, wrong one. That one's better. So under GitHub, there's a place called iOS Weekend -samples. And in there, you'll find something called Swift Intro Playgrounds. And all of the files that I'm playing with on this video are available there, and anyone can download them, and you can experiment with them in Xcode as well. Okay, so our first thing here that we're going to go over today is control flow. Much like in yes, someone's asking, is the GitHub reference in the slides? And it is, yeah. So much like C or C++ or even C# or Java, we have things like for loops and while loops and switch statements, if statements, this kind of thing. But there are some subtle differences in how Swift, in what Swift provides for these different control flow constructs. So I'm going to go through what they are with some simple examples here to show you how they work and what the syntax looks like. We're going to start with something called a for in loop. And the for in is basically the general form of it looks like this: for some element, and you're basically giving an element name there, in, and then you give some collection, like maybe it's an array or a dictionary, or possibly even just a numeric range. Then inside curly braces, you put some number of statements that you want to run, and it loops and it runs those statements multiple times. So the things that make it a little bit different are, at least to begin with, this notion of this range of numbers. So our first example here, for index in 1.5. So that syntax right there is a range of numbers between 1 and 5. In fact, I think I can do that. And you can see that it's a value that has a start index of 1 and an end index of 6, which means it really goes from the value 1 up to the value of 5. So our for loop here is just counting from 1 to 5. And each time it loops through, it's going to print out a message. And we're using string interpolation to print out the value of the index, and then to perform some math and print out the value of the index times 5. And so over here in the console output, you can see that these lines right here are the result of running this for in loop. Pretty handy and sort of a concise way to do that. Our next example here, same thing. It's still going to be a for in loop, but in this loop we've got a bit of an algorithm here that's going to compute some number raised to some power and determine what the answer is. And to do that, it wants to go through a loop for some range, basically from 1 up to the power that it's computing to. But in fact, to do this algorithm, it doesn't really care which index, which value in the loop it's going through. So there's a construct in Swift where you just put in an underscore here instead of the name of a variable. And it's just basically going to ignore it. It's just going to say, you know what, I'm going to loop through this thing for, in this case, 10 times. But as I loop through, I'm not going to tell you which index I'm at. I'm just going to keep looping. And as I loop, then you can perform some computation inside the curly braces here. And that's it. So you can see, again, here's the answer. 3 to the power of 10 is 59,049, which, we assume is correct. Again, string interpolation. So both of those are both of these are basically the same. So I think someone's asking the question, what's the deal with this underscore? Does it really make it more optimized? It saves some memory because you're not having another variable that stores the count index. Beyond that, no, I don't think it makes it any more optimized. It just keeps your code a little cleaner so you don't have some extra value floating around. This same construct will be used later on with tuples and with dictionaries, and it becomes more obvious why it's convenient in those scenarios. In this scenario here, it's sort of it's just kind of a curiosity, basically. It's like, okay, I can do a loop and not care about what the index is. All right, our next thing here is looping over an array. So if we want to create an array, the simple syntax is just in square brackets, put in some comma-separated list of values. And if you recall, an array, I think we talked briefly about this in the section on literals last week. An array, all of the values in it have to be of the same type. So in this case, we've got an array where all the values are strings. And we're going to create a constant called names, which holds this array. Then we are going to use our same for in syntax to loop through the values in the array. And so for name in names, what's going to happen is each time it goes through this loop, it's going to assign a different one of these values, first Anna, then Alex, then Brian, then Jack, to the variable name. And then in the loop, we can use the variable to do whatever we'd like. In this case, we're just printing them out. And again, you can see over on the right-hand side over there that it went through the loop and printed out those four names. Similarly, we can use the for in to iterate over a dictionary. And we're creating a constant dictionary here called number of legs. And it contains 3 different animals and the number of legs they have. So the key for each of these dictionary elements, right? The key is, in this case, spider, which is a string. And the value is 8, which is an integer. So this is a dictionary with string keys and integer values. And we're going to iterate through it using for in. So we're going to go through the first key value pair, then the second key value pair, and then the third key value pair. And so in this case, since it's a key value pair, our iteration is going to use a tuple. So here we've got 4, and then in parentheses, we give 2 variable names, animal name, and then we also give leg count. And those 2 variables will get assigned to the key and the value of one element in the dictionary each time we iterate through the loop. And so then inside the curly braces here, we can just refer to them as animal name or leg count, and we get the values we would expect out of the dictionary. The last example I have here for in is if we just wanted to, let's say we were writing a parser and we wanted to somehow just loop through the characters that are in a string looking for something. We can use for in where we say for some character, and in this case, this is just the name of our variable. Our variable is just called character. For character in, and then whatever the string is we want to iterate over. And what this will do is this will walk through that string one character at a time and assign the value to that variable. So again, over here, you can see that it printed out hello, in this case, vertically. Okay, so that's for in. That's one of 2 for loop constructs that Swift has. The other one is a regular old for condition increment type of a loop, which is sort of the old standby way of doing a for loop in C. It's basically the same syntax. All of the same rules basically apply. So the general form looks like this. We have a for loop. We have an initialization statement or statements. There can be more than one statement before that semicolon, and they could be separated by commas. And then after the initialization, then we have a condition, which is some kind of logical expression that determines when the for loop terminates. And then we've got some statement to increment 1 or more values in the for loop. And then finally, inside the curly braces, just like the for in, we've got 1 or more actual statements of code that we want to run in the loop. So the simplest form of this is something like what you see here. For some variable called index equals 0, index is less than 3, increment the index. And we just print out the index. And that's the simplest version of the for loop. A little bit fancier version of it here, we're going to do 2 variables and 2 increment statements. So for, and we declare one variable called A, and its initial value is 10, and another variable, its name is B, with its initial value being 1. And then we're going to set the condition for the for loop to be A greater than 0. So this loop will keep running as long as A is greater than 0. Then we've got in the increment section, we're going to decrement A, and we're going to increment B. So basically we have 2 counters, one that's counting down, one that's counting up, and we're just going to print them out. And you can see them right here, right? You can see basically what's happening here. One started at 10, the other one started at 1, and they just work their way through their set of values until the condition A greater than 0 is no longer true. And so this was the last line that was printed right here. Okay, so that's regular old for loops. Next thing here is while loops. There's only a single type. Well, I guess you could kind of say there's two while loops. There's a while loop, and then there's a do while loop. They are, I guess, cousins of each other. So the while loop syntax is while, condition, and curly braces. You have statements. One thing to point out about all of these different constructs that we're going through, in no case is it permissible for us to do something like while x less than 10, x minus x plus plus. Get rid of that. You can't write any while loop like this or a for loop or anything. In Swift, these brackets are mandatory. You can't write. I need to actually give this guy a name. Just to keep it happy. So just showing you that basically this opening curly brace and closing curly brace are not optional in Swift. In C or C++, those are optional. If you have a loop that just has a single statement, you just put the single statement there inside the loop and you don't need any curly braces. And that's the source of a lot of programming errors, just mistakes that developers make. And so in Swift, that's something they just don't allow. So you're going to see in all these cases, like this while, condition, curly brace statements, you always have the opening and closing curly braces. Okay, so we're going to create a while loop here that lets someone buy some candy, basically. So we're going to set up some variables, a constant and a couple of variables. The first constant we're going to set up here is the cost of a candy bar, presumably $1. Amount of money in a person's wallet, $6.85. And then how many candy bars they've purchased, which is 0 to begin with. And we're going to go through this while loop. While there's more money in their wallet, it's greater than the amount of one candy bar, the cost of one candy bar. We're going to let them keep going through the loop and buying another candy bar. Okay, so they're going to go through the loop, and each time through, they're going to, basically take money out of their wallet and put a candy bar in their pocket. Okay, and then at the end, we're going to print out these values here about what's left. Nothing really, I think, probably nothing out of the ordinary there if you're familiar with while loops from another language. Do while is similar, except for it runs the statements once before it checks the condition. So we've got do, opening curly brace, some number of statements, closing curly brace, and then the while condition. So here we're going to do the same thing, but we're going to eat the candy bars now. We're going to say candy bars on hand is a variable. It starts out initialized with the value of the number of candy bars the person purchased. Then we're going to go through this do while loop. We're going to eat a candy bar. Now, there's probably a flaw in this logic here, because what if the person wasn't able to buy any candy bars at all? They would go ahead and eat a candy bar that they didn't have, but I didn't notice that until just now, so hey, whatever. Okay, so in this case, they did start with 6 candy bars. They go through this do while loop and subtract one value from the candy bars on hand, and then check the while condition, and as long as there's more than 0 left, we're okay. So take it with a grain of salt. Obviously, there's a bit of a logic error there. Okay, if statements. Again, there's not really anything different than in C here. We have a simple if statement, which is just if condition curly braces statement. Then you can expand it with an else clause. And if you would like to, you can chain multiple if statements together with if, else, if type of a syntax, like what it shows right here. So we have some examples here. Have a variable. If the variable is less than or equal to 32, then we're going to print out a message. Same thing down here, but we've got an else clause in it. Then we've got an example here of chaining, right? We've got if the temperature in Fahrenheit is less than or equal to 32, we do one thing. else if it's greater than or equal to 86, we do something else we do the last thing. And then our final example with if statements is just showing that it is possible to omit this final else, and everything still works out just fine. It's just there's no case for handling that condition, but that's permissible. Our last construct for control flow is a switch statement. This is the one control flow statement in the language that is markedly different than other languages where you've got switch statements. In C or C++, a switch statement typically can only switch on an integer value. Can't switch on a string, for example, which is something that people frequently want to do, but it just doesn't do that. Here we can do that. In a switch for Swift, the value that we want to consider here can be any one of the basic types of the Swift language. So that includes integers, floats, doubles, strings, classes. It's like there's a number of things that we can put in there. Not classes, sorry, structs, and tuples. Okay, each of the cases, the syntax for the value that's going to match is going to be more expressive than what you can see in C or C++. And then you can put one or more statements. You always have to have at least one statement. You are not allowed to do what's called fall through. If someone were to think about something like, oh, come on. I think Xcode's crashing on us. Give it a second. So basically what I want to show you, and we'll see whether or not it'll let us, is what I was just going to type in, basically what a typical fall through looked like in C or C++, right? Where you would have the first case and a colon, and then right after it another case and another value and a colon. You might stack up 3 or 4 of these together and then have one block below it. And what you're basically telling the language is, if the switch matches any one of these 4 values, run the statements below. That sort of a construct is not available in Swift. Let me see if I can recover this thing somehow. It's particularly confused. Well, I guess that's not unexpected, right? Hopefully it'll be back up in a second here. And I think we're back. All right. Okay, so we're back to our switch statements. Instead of me just trying to explain it, let me just show you an example here. So the first example here is a simple switch on a character. We've got some variable here. In this case, it's a character. It's the letter E. And we have a switch statement here that will tell us whether or not this is a vowel or a consonant or some other character. So we have switch, and then this is the variable we're switching on, which happens to be our character, and then our first case. Now, the first thing you'll notice that's different than other languages is we can have a comma-separated list of multiple different matching patterns. So here we're saying if it's an A, E, I, O, or U, it's going to match this particular case. And so if it was a match, which we know that it will be, then it's going to print out this message here. And then notice that there is no additional line here, right? In other languages, you'd be familiar with having some kind of a statement like a break there. That doesn't exist in Swift. Swift has the concept that whichever case matches first, that is the case that will run. And as soon as that case has finished, the switch statement is done. It will exit out of the switch statement at that point. So this means that a certain class of errors that happened when developers used to forget to put in the break between two switches, between two cases, I mean. Sometimes you would get very strange behavior out of your application and you wouldn't really recognize why until you finally realized you forgot to put a break somewhere that you should have. Since that's such a common mistake, Swift is pretty much telling you you'll never make that mistake again because we will not allow it to fall through to the next switch. Okay, so if it doesn't match A, E, I, O, or U, then it's going to move to the next case and it's going to compare the character against all of these. If it matches one of those, it will print this. And then finally, if none of the explicitly stated cases match, then you can also specify a default down here. And the default will be what is run if nothing else matched. One of the things that's a requirement in Swift is that cases must be all inclusive, meaning, or I guess exhaustive, I think is the word they use, meaning that whatever the full range of permitted values are for that variable there, in this case, some character, the compiler must see at least one case that will match every single value that can be represented by that variable. So that means you either have to have explicit cases for every value, or you have to have a default. If you don't have explicit cases for all values and you leave the default out, so let me take this out for a second. So if I take that out, you can see what's going to happen here. Switch must be exhaustive. Consider adding a default clause. Okay, so the compiler is basically just telling us, hey, you've made a mistake here. You're switching on a variable, but this variable could have values for which you did not provide a case. And so they consider that a bug that they don't want to let into the running application. Okay, so that's a simple case. Here's another simple case, but switching on numeric ranges. So instead of us matching a comma-separated list of characters here, we're actually able to match numeric ranges, like this 1.3. So here we're switching on a variable called count, which is an integer. It's a pretty large integer, right? But it's still just an integer. And then based on the case here, we're going to assign a value to some string. And then when we're all done, we're going to print out that string. And so you can see basically just the syntax here is showing us that it's quite possible for us to just specify explicit ranges of values using the Swift range syntax. And the case will match if the value is within that range. Switching with a tuple. So this, I think, is something that would happen fairly frequently if you're writing some sort of maybe user interface or other custom UI that where you're manipulating a lot of points. You may have reasons why you want to compare X and Y values at the same time and sort of classify them into groups. And that's what this switch statement is showing you an example of. So we've got a point here, and the value is 1, 1. And we've got 4 cases and a default here. We've got a case for the point being at the origin. So if the value in this tuple, so the tuple is called some point, and it has 2 integers in it, right? It has what we're assuming to be an X and a Y, but they're not actually named here. So we've got these 2 values, and if they are 0 and 0, we're going to assume we're at the origin. And then if they are anywhere along the x-axis, meaning we don't care what the x value is, but y has to be 0. So in this case here, it's another example of we don't care what the value is, so we're using that underscore syntax again. And so here we can just print out a message indicating we're on the x-axis, and then we do the same thing for the y-axis, where the underscore is on the second member of the tuple. And then we can actually even do a tuple with a range. So we can say, okay, if it wasn't the origin and it wasn't on the x-axis and it wasn't on the y-axis, now let's check and see whether it's in a particular bounding box. Let's see whether it's between the value of -2, -2 and 2, 2 for this box. And so we can specify that very concisely using this range within a tuple. So we say for the x value -2 ... 2, and for the y value the same thing. If none of these match, then we must be somewhere outside of that bounding box. So we're going to print a message that says we're outside the box in the default case. One comment here to highlight. Note that the first match always wins, right? So the value 0, 0, of course, also matches this case, and it also matches this case. But because of the way tuples behave in Swift, we only run that case, and then we are done with the switch. Okay, sort of expanding upon that last thing, we've got this tuple. It has two unnamed values in it. It has the first value and the second value. Well, let's just say for the moment that inside the switch statement, we would actually like to refer to those tuple members not by their position, but actually by a variable name. And we can do that in the case by actually providing a variable name for each element that matches in the tuple. So here, instead of having an underscore here for that first bit and saying we don't care what it is, we're now saying let x. And so we're saying basically create me a constant. I'm going to call this constant x, and you should assign the value that is in the first position of the tuple to that variable. So now inside of this case, I can refer to that number 2 right there by the name x. Okay, so it's like kind of like creating an alias for a position within the tuple. I can do the same thing for the y value, let y, and then I can even do it for both values, let x and y here. So that's a handy way to kind of break apart a tuple, especially if you're getting a tuple as like a return value back from an API call or something. We can actually be more precise in the case statements of a switch by including a new clause that we don't see in other languages called where. And so here we can say, okay, I've got a point. I'm going to switch on that point. I'm going to say case let x comma y. So that first part there is the same as what we saw up above. But now I can say let x y where x equals y. And so this where is like an additional condition that must also hold true in order for us to match this particular case. So we're basically saying, all right, give me the x and y value only if I'm on a diagonal line where x equals y. I can do the same thing for another line that's diagonal going in the other direction, where x is equal to minus y. And then finally, the last thing I can do is I can say, okay, well, if it's not one of those two, then just give me the x and y values out of the tuple. So that where clause is pretty interesting. Let's see. So is this where clause kind of equivalent to the double and in an if clause? Not really. Yeah, I don't think there's a whole lot of similarity really. I mean, they are two separate logical expressions. I mean, I guess, yeah. I mean, in a certain sense, I guess you could say that this is like an and, right? This has to be true. It has to match this thing, and whatever's over here has to also be true. That's I think a fair statement. Okay, so we've looked at the control statements that we've got. Now, one thing that I didn't show you, but that is available in the language as well, is there are times when you're in these various control statements inside one of those blocks of code where you want to short circuit things, where you basically want to say, okay, I don't want to run this for loop anymore. I'd like to break out of it, or I would like to stop this iteration and have it continue directly to the next iteration in the loop. There are 4 control transfer statements in the language. There's continue, break, fall through, and return. And the first couple, continue and break, I think anyone who's done work in C will already know what those are. Fall through is unique. It's where you can actually say, put the keyword fall through in a case, and it will actually say after this case is done, fall through to the next case. Then return, you know what return is. It just returns out of a function, possibly passing back a value. But you can do that from inside a loop, and it'll short circuit the rest of the loop. Okay, so that's it for control flow. Let's move on to some of the things we can do with strings. Okay, so we saw some real basic stuff about strings last week. We can declare a literal string. So last week I had this literal string by itself. Now I've got a constant called message that stores that string. You can see that you can escape certain things like the double quote, or you could even like escape a new line there. So now that string is technically 2 lines long. So stuff like that. You can do string interpolation. So here we can create a constant that contains the string 2 plus 2 equals, and then inside that \paren thing, we can put any sort of expression we want, and it'll perform the math right there. And so it creates for us a string 2 plus 2 equals 4. We can create a variable with a string, same as the constant, except for it's a variable. Strings in Swift are full Unicode strings. So here's 3 examples of creating Unicode characters by their code point. So the first one is a 8-bit code point for the $sign. So basically that's the equivalent of like the ASCII value for it. Black heart here, that's taking a 16-bit value from the Unicode code set, and Swift knows which character that is, so you can see that when it actually prints out, it's the single character of just the heart from the card deck. And then there are some expanded code pages beyond the default 16-bit Unicode. And one of those has a bunch of different emoji characters in it, and this is an example of writing in one of those to get that red sparkling heart. Okay, so let's see. If we want to create empty strings, there's a couple of ways to do that. Probably the most natural way for someone to think about it is you just create a variable or a constant and you assign it a value with just opening and closing double quotes and nothing inside. That creates an empty string. You can also do the same thing by just creating a string and assigning it an instance of the string type with no initializer in it. Okay. And once you've got a string, you can test whether or not it's empty by taking that string and running the isEmpty property on it, and it'll return true in the case of our empty string. And in the case of that heart, it returns false. Notice that isEmpty is not a function, right? It's just a property. Okay. Mutability of strings. Remember, if we have something that is a constant, we declare it with let. And if it is a changeable string, we declare it with var. This is different than what you are used to if you program in Cocoa in Objective-C, either for iOS or macOS, right? You're used to something called NSString and something else called NSMutable string, meaning changeable string. In Swift, those concepts they're not, that concept isn't created by having two different classes to implement the different types of strings. Instead, right, it's built into Swift with this let and var concept. So if we want to create a string that we can actually change, we have to do one of two things. We either create the values as part of the assignment to a constant, which is perfectly fine here, right? So we're taking the first string and we're adding a space plus the second string, and we're getting the full name, but the full name is a constant here. Or we can create a variable, and then once we've got that variable, we can take that variable and we can add things to it. In this case, I'm using the plus equals to add the full name to it. So that's sort of your basic building blocks for appending things or concatenating things together in strings. Swift defines strings as being a value type. And what that means is strings are always copied when they are assigned. They are not shared. And so this little bit of code here is attempting to show an example of that. So you can see that we've got S1 has the value hello in it. And then we're going to create another variable, S2, and we're going to assign it the value of S1. So they clearly both have the same value right at the moment. And if this code here, if it's true that these are value types, then if I change one of them, only that one should change, not the other, right? So if I change S2 to be the word goodbye instead of hello, and then I print out the two values for S1 and S2, you can see that S1 is still hello and S2 is now goodbye. If you were to do something similar to this in Objective-C, this is not the answer you would normally expect to get, because in Objective-C, strings are reference types, so these would have both been pointers, and when we change the value to goodbye, it would have actually changed both of them to be goodbye. Okay, so all of the elements in a string are of type character. You can iterate over them. I already showed you how to iterate when we were talking about for loops before, but here's another example of the same thing. All I'm trying to drive home here is that, in fact, the string can include characters of different sizes because some of them are different size Unicode values. And in terms of how this loop works, it's just as you would expect. It just prints them all out. Let me actually go back here. Yeah, here we go, right? Those are the values. Okay. Next thing, if we have a string and we want to know how many characters in that string, there is a global function called count elements. You can use it on a number of different types. Here we're just using it on a string. And so we can say count elements for the proper name, and it shows us that there are 17 characters in it. Count elements for the sparkling heart shows us there's only one character in it. Once we have some strings, we're going to want to do comparisons. We're going to figure out whether they're equal to each other, not equal to each other. So the normal double equal sign tests equality, not equal tests whether they're not equal. So you can see the two values here are what you'd expect. They also have a method to allow you to pull off a prefix or a suffix from your string. Those methods are just called has prefix and has suffix. And so we're testing to see whether it has the prefix. And obviously strings are case sensitive, so this first one here fails, right? Ben in lowercase does not match the first part of my name, but with an uppercase B it does, so you can see the results over there. And then a suffix, same syntax, but just has suffix, and it matches in this case. Let's see, last functions we'll talk about with strings right now are uppercase string and lowercase string. So these are just simple properties that will get you a new string. They do not change the existing string. They get you a new string that's either all uppercase or all lowercase of the original string. And then finally, all I've got here is I've got some examples for you of what you would need to do if you wanted to actually walk through the Unicode characters in a string, either as UTF-8 or UTF-16 or as Unicode scalars. And the way to think about it is each of these is just a for in, but instead of looping over the dog string here, they're looping over a property of it. And for UTF-8, the property is .UTF-8, .UTF-16, or .Unicode scalar. You can see that the answers are different over here. they are based on which character it is. Obviously, for the capital D in dog, it's the same in all three examples. But for some of the other Unicode characters, especially the dog at the end, you can see that it's different values in all three cases. And those are just three different encodings of how you would get to the Unicode character. Any questions about strings? Okay, let's go on to collections then. We've got a little bit of time left. Okay, so Swift has two types of collections for us. It has arrays and it has dictionaries. We've seen each of them briefly in earlier playgrounds, but here we're going to just kind of go through all the capabilities of both arrays and dictionaries. I think we all know what an array is. Basically, it's going to be just an ordered set of values who are all of the same type. We can declare an array. The sort of a longhand version of declaring an array is with this syntax here: array, angle bracket, and then you put the type in the middle here, and then closing angle bracket, and then opening and closing quotes. So that declares an empty array of type int. There is a shorthand in the language to let you also declare an array, which is to use the square brackets. So array, square bracket, square bracket. That declares an empty array as well. And then if we want to create a literal array with some values in it, in this case here, we're creating an array of strings with 4 different pet types in it. And then below it here, we're actually going to create a variable called pets, which is of type string array, and we're going to assign it to those values. And note, we could leave off the type, right? Because of the way Swift does type inference, we could just do this. We could take that completely out, and that's still the exact same thing. It means the same thing. It's just, it's just relying upon the type inference in Swift instead of the developer to explicitly state what they intended. Okay, so once we've got an array, we probably want to know how many elements are in it. So there's a property called count. In this case, it reports there are 4 elements. Just like with a string, if we want to know whether or not an array is empty, let's see. Is the question whether or not declaring the type or doing that is faster? Is that what you're asking? Basically, they are identical. It is just syntactic sugar. It's not going to change the runtime performance either way. By the time it's compiled, it's going to be an array of strings either way. And I think type inference is one of those things where some people are going to really like it, and other people are going to want to be more explicit and write out their lines of code like what I did here. I'm kind of on the fence. I don't know which one is what I will end up doing. There definitely are some cases where it becomes harder to think about your program if you have to always remember in your head what type was inferred into something versus being able to just look at the line of code and go, oh yeah, that's a string or that's a float or whatever. But yeah, it's early days, so I don't know. I could end up using type inference everywhere. But for now, I'm personally more comfortable with actually declaring the type here just so I see it when I'm looking at the line of code. No performance difference, though. This one here, that guy, is that the literal string you're wondering about? You would not. The only reason why I did that was just so that in the playground here, we can show you the simplest form of creating a literal string. Yeah, it's not something you would write in code at all. Okay, so we want to be able to test if it's empty, so we can use this isEmpty property. Now, a natural thing for us to want to do with arrays is to add more elements to the array. There are 2 ways we can do that. We can do that by use of a function called append, and we can say pets.append and give it a new string, and it'll add that string. If I try that, it's going to give me a type error and let me know that it's not possible to append the value 10 because it's not of type string. Okay, so it's very much the case that these are type safe collections. So I append fish, and then I'm going to add an element a different way by using plus equal to add a horse. And when we're done with that, you can see that our collection has, there's the fish, there's the horse, right? All the elements are in there, or all the pets are in there. And our count has now gone from 4 to 6. If we want to access individual elements of the array, square brackets work. So pets sub 0 is a dog, pets sub count -1 is a horse. If we want to change an element, we can do assignment to the subscripted element. So pets sub 4 is a guppy, so I think we're changing the fish into a guppy. Or we can insert an element. So we can say insert a hamster after the index number 2. So some of these operations, like this insert here, would change the size of the array. Some of the other operations would keep the array the same size, like just changing a particular one of the elements' values. If we want to remove something from the array, we can use remove at index to remove a specific element, or we can use remove last to basically just pull the last element off of the array. Iterating over the array, simplest way is a for in loop. We saw this earlier. For pet in pets, we're going to print out each of the pets. So that prints us that first list right there. If we want to erase everything out of the array, oh, sorry, I skipped ahead. We can also do an iteration of an array where we are going to get a tuple, and each element of the tuple includes both the index and the value. And this is a convenient way if you know you're going to do something with each element, but you also need the index to where you are. There's a global function called enumerate, and you can pass it in your array of pets, and it will return for each time we enumerate the next element, it'll return a tuple with the index we're at and the value at that index. And so that's how we produce this list right here. Okay, to empty out our array, we can simply assign it to an empty array. That is the easiest way to destroy all of the contents of the array. Alternatively, if we want, we can use a function called remove all. And one of the things that remove all has is it has a parameter that lets you specify whether you want to keep the capacity. So if you have an array in memory where you've maybe allocated 1,000 elements of, say, doubles, and you know you're going to use that same 1,000 elements again after you erase the array, you would probably want to set this keep capacity to true, and it would erase all the elements, set them all back to 0, and it would let you then use the array for something else. Whereas this version here quite possibly collapses the size of the array. They don't tell you what the exact behavior will be, but you shouldn't expect that you would still have an array that is pre-allocated to a particular size. Let's see. We also have an ability with arrays when we initially create them to initialize their content to some predetermined value. Now, the default behavior in Swift is that whenever you create a variable, it's initialized to 0. And that happens whether you're running a debug build or a release build, doesn't matter. It's always going to be initialized to 0. But you might want an array that's all initialized to some different value. And so they have a syntax for that when you originally create the array. So here I'm creating an array of doubles, and I'm going to set the size of the array to be 10 elements. And I want each of those elements to have the value of pi in it. So I end up with an array with lots of pi. Okay, so this last bit here on arrays is where things get kind of tricky. So we're going to deal now with mutability of arrays. So I'm going to start with an array that has the values 1 through 5 in it. It's just some integer numbers. Notice I created it as a constant, right? I said let numbers equal. I didn't say var numbers equal. And Immediately after that, I'm going to say numbers sub 1 is equal to 10. And the compiler doesn't complain about this. Okay? This is intentional. This is the behavior that they expect. When you declare this numbers array as a constant, what you told the compiler was the array cannot change in size, but the elements themselves are not constant. So it's kind of a weird thing. In Objective-C, we have the concept of an NS array and then another thing called an NS mutable array. And when we create an NS array, the elements are constant. We cannot change them. Well, that's not the case in Swift. In Swift, when you create this array, only the array variable itself is constant. It's going to always point to this array, and this array cannot change size, but the contents can change. So here I changed numbers sub 1 to the value of 10. If I try this here, and I try to actually append more lines of more integers to it, that does fail. Okay, so the compiler says you can't do this. And the reason you can't do this is because in order for it to make that change, the array that the variable numbers points to would have to change in size. It would have to be one element bigger in order to store the value 10. And so the compiler doesn't allow that. Okay, so now we're gonna play another game with the arrays. So we're gonna create an array. This time we're gonna create a variable called A1, and it's gonna contain the contents of our original array. Now we're going to create another variable called A2, which also points at A1. So you can see they both have the same values in them right now. We print them out here, just make sure we're all on the same page. There is an equivalency operation, which is 3 equal signs, which asks, are these two objects pointing at the same thing? And right now, A1 and A2 are equivalent, meaning they are not just holding arrays that have the same values in them. They are, in fact, pointing to the exact same array in memory. Okay? There's only one array in memory right now in A1. A2 points to the same thing. Now I'm going to perform an operation on A1. I'm going to add something else to that array. So I'm going to grow its size by one more element. So A1 append, and then you can see A1 now has 100 on it. And A2 still has the original elements. Now look what our equivalency operation tells us. A1 equivalent to A2, no longer true. The reason it's no longer true is because we changed the size of A1, and the minute we changed the size, it made a copy of the entire array. Okay? So that allowed A2 to continue pointing to the old array that only had 5 elements in it. And A1 now points to a completely different array that has those original 5 elements plus the new element with the value 100 in it. So now if I take A1 and I remove the last element, so I remove that 100 off of it, so now A1 and A2 actually have the same values in them again, but my equivalency is still false. And that's the way we would expect it to be, because each of those two arrays are pointing to completely different places in memory now. They just happen to have the same values in them. But if I test for just plain old equality between the two arrays, they are actually equal, because equality is testing the values of the elements within the array, and it says, yeah, those are the same, they hold the same values. They're not pointing at the same place in memory, but they are the same values. So that's kind of a tricky thing about arrays. You just have to kind of get used to. Okay, we ran out of time today to get through both arrays and dictionaries, so we'll pick up with dictionaries next week. As I mentioned earlier, we've got practice files for all of the presentations in the GitHub repo, and you can get at those in the repo listed on the screen here. Open them up in Xcode 6 Beta 2 and get started playing with everything you see in the video. Thank you very much for joining us today, and I hope to have you join us again next week when we pick up with dictionaries and then get into enums, structs, and classes. Have a great day. Bye-bye.